Ready? Okay, wow, let's get started. First, good afternoon, everyone. Welcome to our coffee hour lecture series hosted by Department of Geography. So today we are so honored to have Dr. Richard Alley as our speaker. So before I introduce Dr. Alley, I'm gonna first announce some good news from our community. We have a long list. so, so first, undergraduate geography major and millennium scholar, Rasha Al-Wakil, was elected president of the 20th University Park Undergraduate Association Assembly. Congrats. Undergraduate Daniel Dido received the College of Earth and Mineral Sciences, J.M. and Catherine Tiffany Award for Outstanding Student Leadership and the Alan Stidel Achievement Award. Congratulations. Congratulations to graduate student Natmi Batigay for passing her qualifying exam. Congrats. Adam McConan, a dual title geography and African studies PhD candidate, had their article Review CUNY Distance Learning Archive published in Reviews in Digital Humanities. Congrats. Our PhD student, Nafisa Anjum, and her husband welcomed their first child, a boy named Kazi Nawa Anjum, into the world on Saturday, March 22nd. Congrats! Our associate professor, Broven Powell, was honored with Charles Hausler Diversity, Equity, and Inclusion Faculty Award by the College of EMS. Congrats! Our assistant professor, Mark Otis, received a Gladys Snyder Faculty Enrichment Grant from the College of EMS. Congrats! Brady Watkins and Michael Coupland were members of the winning team at the AAG's World Geography Bowl. Congrats! I'm sorry the mispronunciation if I mispronounce somebody's name. Sorry about that. And Lily Hartman passed their PhD proposal defense today. Congrats, Lily. Okay, now it's my great pleasure and honor to introduce our today's speaker, Dr. Richard Alley, Evan Pugh, University Professor of Geosciences and Penn State. And Dr. Alley earned his PhD from University of Wisconsin in 1987 and has since become one of the world's leading scientists on ice sheets and their role in climate and sea level changes. His groundbreaking research on the Antarctica and the Greenland ice sheets has earned him numerous honors for scholarship, teaching, and service, including elections to the U.S. National Academy of Sciences and Royal Society. And this January, he received the U.S. National Medal of Science. He was a key contributor to the United Nations Intergovernmental Panel on Climate Change, which also shared the 2007 Nobel Peace Prize, and he also requested advice to high government officials from both political parties. And Dr. Alley has authored or co-authored over 400 scientific publications, and he is also known for his scientific communication with very broader audiences. He was presenter for the PBS TV mini series Earth, the Operator's Manual, based on his own book, his popular account of climate change, and Ice Course, the 2-mile time machine was a Phi Beta Kappa scientific book of the year. Last but not least, he is happily married with 2 grown daughters, 2 stay-at-home cats, a bicycle, and a pair of soccer cleats. Okay, please welcome Dr. Alley. Give a talk.
Oh, thank you. I got it here. Thank you. Oh dear. So great to see so many old friends and new friends. So thank you, Shuja. It's truly an honor. So thanks to the Department of Geography and to you for coming. If you see a penguin, is to lighten up. You had all this good news. I'm going to give you bad news. So if you see a penguin, it's just try to lighten it up a little bit. Okay. I hope you all know what a powerhouse your department is in the world of ice. And I have a couple of professors on here and some of the grad students who are doing something with Shuja and Luke and Shuja and your grad students. You really are. And people like Gita Cervoni, who is interested as well. You have a long history of being really good in this field. Across the street, we think we're okay too. And so I know Don Voigt is in the back over here. At any rate, here's a few of our people in the field. Knut's a professor at Washington now. Rebecca went in the real world. Luke's a professor at Wisconsin, so on. So current grad students, although Thomas just graduated, he's working on how the melting of the ice in Iceland is making the volcano erupt more. And he has a desk that he can peer around the corner and see the volcano erupting. Well, yeah, anyway, and the rest of these are going to go off and do great things fairly soon. So for what it's worth, a couple of other slightly older folks here who have contributed to this, and you will see some of their work coming. Sridhar's on sabbatical, but this is he and I back when my beard was red. He looked exactly like that. He hasn't changed a darn bit. But anyway, so what we're going to do here is walk through the fact that sea level rise is virtually guaranteed. There's just no way out of this, okay? But it could be a lot more than we've been expecting for well-observed, well-known, really, really hard to model processes with threshold behaviors. And this matters, okay? So that's where we're going. I was out at the middle school here 2 weeks ago and talked to 150 students, and I was down at the high school, and so when I do those talks, I run through these slides. The penguins are great. I'm sorry, but this guy is just so good. But what I walk them through is that there still is hope, and that if you took the IPCC, if you took the UN, I'm going to rag on the UN. I'm going to tell you all kinds of things that they may have done wrong, but they're fantastic. They're valuable. They're useful. And if you took all of those reports, starting with the first assessment in 1990, and you turned them into a very short statement, it would be this, which is that if we use our knowledge on climate and energy, we get a larger economy with more jobs, with healthier people in a more secure nation that is more ethical and more environmentally clean. Right now, it doesn't matter what you care about. It's in the same direction, which is using our knowledge. And the truth is, this is my dad joke, right? I'm a dad. We can turn this around. The truth is this generation is the first one in human history that knows they could build a sustainable energy system. And they can make enough energy that you do not have to impoverish your country importing a fuel all the time. And you can get it for everyone. And you can do it the way that works for your country, where you are with your resources. And that's never been true in human history. All right, so there is good news we can do. But if we don't do that, the sea is going to rise, probably a lot. Okay, so here's data. This is satellite altimetry pieced together from a lot of satellites watching the ocean surface come up. Not that much, but it is coming up and it is accelerating, and that's real. And it already matters, okay? So I've stolen these from the web. I've shown them a few times around campus, right? This is not a storm, it's a high tide. This is not a canal, it's a street. This is what they call adaptation. You don't want salt water on your plants because it'll kill them, and you don't want people driving real fast through the salt water to kill your plants, so you put up a no-wake zone in the middle of the street. Okay? This is from the Miami Herald. This is an octopus. The octopus, it's a high tide, it's not a storm. The octopus was not brought here by Penn State hockey fans or any other hockey fans. It swam in, right? And they call this nuisance flooding, but if you're any engineering background and you remember the condominium pancaking and you look at the salt water on the supports for the building, you might get nervous. but they still call this nuisance flooding. And then at some threshold, it isn't a nuisance anymore. It's really expensive. And so you get a lot of this, well, the first bit of warming was pretty cheap. Won't the next bit be cheap? No. Okay, we had adaptive capacity, we've used it. All right, so that's important going forward. This is Philly, and the thing at the bottom here, starting in 1920 and up to 2020, is how often they have somewhere this kind of high tide flooding. And then the blue curves start in 2020 and they go into the future. How often will Philly have high tide flooding in the future as we drive sea level up? And I hope you can see we've used the adaptive capacity. Now it gets bad. And it can go up a lot, especially if we crank sea level up a lot. This is a map of Philly. And somewhere in here, that right there is the Philly airport. Okay, so over there, that's the Philly airport right there. Everything in color here goes underwater if West Antarctica goes. Okay, if we don't build walls. And there's colors on here where they think we build walls and where we just let it go under. But nonetheless, if you scale the Philly airport, which is that little corner, and then you say everything under there goes if West Antarctica goes. All right, so back to the data. We put the previous slide now on the past and future for a longer window. And so the previous slide is that pink one. And the various things in there that are quantified are low warming, middle warming, high warming. And then the dashed line is unless something bad happens. Okay, so this is the most recent IPCC. Nice, well quantified, carefully done, lots of really, really solid science in the bars and the colors, and then the threshold of if something bad happens to an ice sheet. Okay, this makes planning hard. Be honest. So let me walk you through a little story. I'm going to start with some economics, which I'm not an economist. And then I'll try to get to some glaciology, and I may be a glaciologist. So here's coastal erosion. And economists say, yeah, that matters. But a whole lot of the literature in economics says it doesn't matter a lot. And the reasoning goes something like this, okay? We will get one of these, we won't get the bad thing, and we will respond to it in an efficient manner. So you know how this works. I don't know how Luke affords the beautiful beach house that he has, but he can sit at his beach house and watch the sun go up or down, depending on which coast it's on. And so, but he knows the sea is rising. And so he quits maintaining his beach house. And when the sea finally takes his beach house, it wasn't worth much anyway, except for the view. And Shuji bought the one across the street. And so when his gets out of the way, she has the view. So the economy has not lost the view. All it's lost is a little thing that was not maintained anyway. So it's dirt cheap, right? You will find, I can find the references, that projections for the entire loss to the entire nation's coast for the next 100 years are small compared to the cost of one hurricane. Serious published economic literature that says we are so efficient in responding that it just isn't a big deal. Right? Okay. Now, it is still true that if you run the integrated assessment models forward, that they say we are hurting the economy because we're not investing enough in heading off climate change. This is Bill Nordhaus's Nobel Prize in Economics. It is true we are underinvesting in climate change, but the economists mostly say don't invest a lot. Mostly you invest in a broad economy. Your grandchildren are incredibly wealthier than you are. Money solves problems, so the problems you leave them, they can solve with the huge wealth that they have, which dwarfs what you have. You don't want to work too hard to help your grandchildren because you're a poor person helping rich people. Okay? This is true. I'm sorry. But we would do more now. We would work harder to get rid of climate change if sea level rise could be larger or faster or less expected than what they're using in their model, or if our response is less efficient. All right. So what I'm going to show you very briefly is my personal opinion that there's no chance that we're going to respond efficiently, and then my great concern that sea level rise will be larger, faster, and less expected. And what that leads to then is much greater value in heading off climate change now. Okay, so that's where we're going. So the question about will we respond efficiently? I'm old, right? I used to have a red beard. I do not anymore. I was teaching here long before Katrina took out New Orleans. Every serious teacher in a general education course in the US who taught about the coasts was teaching more or less this. Sea level is rising. New Orleans is sinking. The protective delta is eroding. The storms may be getting stronger. And if you're going down and it's going up, that matters to planning for coastal defenses. We all taught this. It was totally, I learned it when I was a student, okay? And so what did we do? Is that efficient? That was 300, Katrina was $300 for each person in America, okay? And it was lives, and it was property. And these new studies showing that death rates are elevated for a decade after a big storm. If you haven't seen this, this is important, okay? These are huge disasters. And does that look like an efficient, and then, right? So what did we do? We provided high-end storm surface estimates. The engineers built structures to protect. The people were told it was safe. You can go there now. So they put their lives and their properties and everything else there. They built new things. They settled in New Orleans. And then the system failed, right? And yeah, mostly I think it was an engineering failure. It was not that big a storm when it hit. It wasn't that high, but there's enough blame to go around, okay? And so when you see these cost estimates going on, they have been doing sort of likely that we're economically efficient, the costs are low, and sometimes they do a worst case where we lose all the valuable things in the flooded zone. But what did Katrina do? We paid to build the fences. We assumed we were safe. We built new valuable things behind the fences that supposedly made us safe, and then we lost everything. Right? So the worst case is probably a whole lot more than the valuable things near sea level. This was something that came from All Things Considered. It's transcribed here. New maps label much of New Orleans out of the flood hazard area. It's a bureaucratic magic trick. At the stroke of midnight, the federal government waved its wand, and Friday morning, half of New Orleans woke up safe from storms and flooding. Right, okay, so that's part of this. If that is correct, we are very much underinvesting in reducing global warming because the cost of sea level rise will be higher than we're assessing. Now we'll go to the second piece. Are we really confident about this, or could it be that? And I have added a thing there. There's no way that that dashed line is a worst case scenario. Don't go there. It could be a lot worse. So that's where we're going to go. So I can show you the published papers. Andrea Reed Garner did her PhD in Medio here. Some of you may remember her. She went back and did a historical analysis. Let's look at the IPCC projections. Let's look at the underlying literature that they were summarizing. And across the board, the high numbers disappeared when it got to the IPCC. The low ones are there and the high ones are not. Okay. We can compare the rise that happened to what was projected for the earlier IPCCs. It just comes in at the 2 sigma level. So the rise that happened is about 2 standard deviations above the expected, but it's always above, not below. I can show you the scholarship. Some of you may know this, Discerning Experts, the work led by Michael Oppenheimer, on why the IPCC set up, if it works properly, if it works the way it was set up, it will tend to lose these high numbers and come out a little bit low when there's large uncertainties. Okay, I can show you how the models that are being used have left out a lot of really hard to model processes that would all tend to increase the sea level rise. And I can show you some of the recent models and how they have tended to underestimate what happened. And so I can pound on the table. There's no chance that the IPCC is being alarmist, just no. And there's a reasonable chance that they're on the low side. Okay, so this is all. If you want any of these, I can get them for you. I can get you some more. Okay, so back to the data. What's going on? Why is sea level rising? More or less, it's a third the ocean expanding as it warms. It is more or less a third melting of mountain glaciers that takes water and eventually gets it to the ocean. And it's more or less a third ice sheets, mostly melting of Greenland on top. So this is mostly things that Luke studies. This is mostly meteorology, mass balance, important issues in this sort. There's a little bit of groundwater depletion, which is a little worrisome. There's a little bit of taking water out of the ocean and putting it into reservoirs. And there's a whole bunch of local things, which are really, really exciting and fascinating. But that's the big picture. But what could it be? If you melt every bit of ice in every mountain on Earth, sea level is up about that much and you're done. There's nothing else you can do. If you warm the ocean by 1 degree C, it's up about that much, and it could be that or it could be that, depending on whether you're heating warm water or cold water. But it's only 2 degrees up from the Ice Age. The mixing time of the ocean is really long. It's hard to make huge changes in the temperature. And so I've got 2 bars on there in red and blue, which are, this is what you could do to sea level rise from the causes which are 2/3 of the rise now. And then Greenland is 24 feet and Antarctica is almost 200. Okay, so if we're arguing about these, if these matter, we dodged the bullet, we're fine. Okay, it is very, very clear that because ocean water expands when it gets warmer, and because ice melts when it gets warmer, that we can't not have these little ones. The ocean will expand, the mountain glaciers will melt. And so it really can't be better than the IPCC says. But the IPCC projections, those colored bands, under the strongest warming by 2100, lose 0.2% of Antarctica and 2% of Greenland. So their worst case, it's quantified properly, 0.2% of Antarctica, 2% of Greenland. It's really easy to make it worse with the big ice sheets. It's really hard to make it better with anything else. Okay? So let me teach you glaciology. So we teach this class sometimes when we get enough students. And this is Kirk Coffey. He was an undergrad here at Penn State. He's now a distinguished professor at Berkeley. And he wrote the textbook in our field, The Physics of Glaciers. And we would walk through this. So this is some of the things that you would get in a real glaciology class at the graduate level. And some of it's really fun, and it's very interesting things, and we could have a ball, okay? I'd love to, yeah. Anyway, what we're going to do, though, is the 101 version. A few of you have seen these slides, but this is my wife making pancakes. That's her sleeve right there. And so she's making a pile of pancake batter, and what does it do? It spreads under its own weight. Why? Because the weight of the pancake batter makes the pressure underneath a little bit higher than the pressure outside. And so it spreads because there's a push from that higher pressure. That's all you really need. All piles tend to spread under their own weight. They will stop spreading if they're strong enough. So this building tends to spread under its own weight. You do not have to run out. You're fine. It's strong enough. Okay? They will not spread if you hold them back. And they will not spread as fast if you forget to spray the PAM on there. If it's bumpier or less lubricated, they don't spread as fast. Okay? So let me now take you to Alaska. If you've ever been to Juneau, the airport is right down there. And the cruise ships go right there. So the airport is there, and there's the cruise ships, and this is a big waffle. Okay. So it has snowed on top of the mountains faster than it's melted. The snow has piled up. The weight of the snow squeezes it to ice. And when it gets thick enough, even though it's a solid, it flows slowly under its own weight. It's deforming by dislocation, glide, and some other things. And so it is spreading down off of the peaks and then melting at low elevation. It's on a waffle iron, and some of the big flows through the grooves in the waffle iron, we have named things like Mendenhall Glacier or Taku Glacier. So the named glaciers are just big grooves in the waffle iron. Now, if you go up on top, this is Don Voigt teaching at the Juneau Icefields Project, and Kaya Riverman, who's a Penn State grad who's now a professor in Oregon. That's what it looks like in the real world up on top, but it's just a big waffle, okay? And these things are just humongous big waffles, okay? So this is what we're going to have to deal with. We do all of this, right? So this is a thin section of ice. It's a very thin piece, about 4 inches by 4 inches. It's between cross polarizers. The individual snowflakes have turned into those grains you see. Don Voigt did this one. This one is from way down in West Antarctica. The fact that they're all sort of the same color tells you the crystals are aligned. That gives us information about the history of flow. It gives us information on how easily it can flow now. These things can change. They evolve over time. We write papers on this. We've had grants on this. We think this is really, really exciting. And we don't think it's going to change fast enough that you really need to worry about it. So we're just going to write over this one. Okay. The waffle iron, lubricating it, the PAM, we worked, so when the ice flows over the bumps, sometimes it pushes and pulls and you get little surface reversals. And if it melts, the water pools in those surface reversals. So you can see a lake up there. That's in Greenland. This is on the edge. It's a mile across. It's 30 or 40 feet deep in the middle. And we did some work on this, and we said, you know, that's trying to wedge open the cracks. And if it wedges open the crack, it'll drain to the bed and out the front really fast. And thank goodness, Sarah Das, who graduated from here and is a professor at Woods Hole, MIT, thank goodness she was not on the lake in her boat when it drained, because it did twice Niagara into the ice sheet for an hour. And it was making earthquakes, and there's blocks flying. So these pictures, the lake is there. Sarah is in the lake. It's a different one, but it's the same thing. Sarah is in the lake, and it went down that crack. Okay, this is fantastic. It is, talk about exciting things. But the ice sheet changed its flow, but it didn't fall in the ocean because there's a waffle iron under there. It's not a grease griddle. So I'm not going to tell you about that either. What I'm going to do is go back to this one. So this is our spatula, Cindy's spatula. And then I'm going to change analogies or add an analogy. This building is not going to fall apart in the near future. The builders of the early Gothic cathedrals pushed it a little close. And the tendency of the walls to bulge and the roof to cave in actually was taking out Gothic cathedrals. And so they had to develop the flying buttress. And all the flying buttress is that. Okay, and the spreading tendency is being pushed back by holding up that way. And so there's some flying buttresses. And now here's a flying buttress for an ice sheet. All right. And both Luke and Shuja study these. The ice spreads down to the ocean. If it's really cold in the air and the water, it doesn't immediately break off. It spreads over the ocean. It runs aground on a high spot, or it scrapes past the walls of the fjord. It generates friction, which holds back the ice shelf, the flying buttress, which holds back the big pile. Okay? It is minus 50 on top in Antarctica. It's not going to melt when it warms up, but it's almost melting on top. Sometimes it is on top, and it's melting most of the time on the bottom of the ice shelf. If you knock out the flying buttress of the Gothic cathedral, it can fall down. If you knock out the flying buttress of the ice sheet, it can too. Okay? So this is a glorious map from First et al. 2016. Everything in brown is the flying buttresses of Antarctica. We sort of kind of picked the color scheme, okay? Why did we make our ice yellow? Because, anyway. So everything in here in yellow is a flying buttress. And almost all the ice leaving Antarctica goes through these. The places without them are going pretty slow. Okay? And I'm going to take you to that little pink square in the upper left corner there along the Antarctic Peninsula. And this is that little pink square in satellite remote sensing. 12-mile scale bar on the right. The ocean is black. The mountain range is the extension of the Andes. It's gloriously beautiful and big glaciers dripping off of it. And in between there is the flying buttress, which is called the Larsen B ice shelf. It formed about 10,000 years ago as the ice shrank from the Ice Age. It sat there for 10,000 years as of January 31st, 2002. And you remember Sarah's Lake. Well, all those little blue blobbies on top there are lakes like Sarah's. Not quite as big, but they're lakes. And you remember what Sarah's did, it broke through, but the ice sheet didn't fall in the ocean because it's on the waffle iron. Well, there's fish underneath there. This is floating. And so we'll get rid of the labels, and this is 5 weeks. So the thing sits there for 10,000 years, and then it retreats at 10 kilometers a week. The retreat rate is 500 kilometers a year, except it was gone in 5 weeks, so it couldn't do it. 500 kilometers a year for retreat rate, right? This is Susie's paper, we are making a lot of gain in understanding how this happened. What are the early warnings? How would you start putting this into a model? But it's still really challenging to put this into a model. Really challenging. Okay? So let me do it for you again. We're going to go to Greenland. We're going to come in along that yellow arrow. So everything, we're going to look in along the yellow arrow. And we're going to look at this blue one, which is the really deep groove in the waffle iron of Greenland. It was the fastest flowing groove on Earth. And then the ocean water warmed by about 1 degree for interesting reasons, but nonetheless, it warmed by a degree, mostly circulation things. It had an ice shelf. The ice shelf broke off. It had been the fastest glacier on Earth. It tripled. Okay. So here it is. We're looking along the yellow arrow. You can see that. The blue is the waffle iron groove flowing towards you. That's Jakobshavn. The thing in between is broken up ice on top of ocean water, which is going down a ways. There's tundra on the right, tundra on the left. And I'm going to show you 2 pictures. First picture, second picture. So first we're going to go in over the ocean water, and there's a seal. Okay? So yes, there's ocean water under there. They do science with these seals. They put instrument packages on them. They swim around under the ice. They come back up and telemeter the data. And then I'm going to take you in, and the seal was down a little farther out, but the seal was in the seal down there. The blue arrow is the same blue arrow. So this is the non-floating ice flowing out. And the cliff is about 100 meters. So a 30-story building. I was down in Philly here a week or 2 ago, and so I used Independence Hall from Philadelphia. So there's Independence Hall, and there's Independence Hall to scale. Okay. Now remember, it's 9 times more under. This is almost floating. So it's 9. So that's a half of Independence Hall, but there's 18 Independence Halls below sea level. Okay. This is big. I mean, it is really, really, really amazing. Okay. So this is in close, and I have told many of you this story. At one point, I got to go to Greenland with 10 U.S. senators. And we are in the helicopter. I've got the headset on. And we've got senators in the back. That crack is 10 stories high. Right now, if you walk downtown and you looked up and you saw a 10-story high crack in a 30-story building, so the pilot says, "How close do you want me to get?" And I said, "These are senators. Pull it out a little bit." So this is what some friends sent me these pictures. This is what happens. So I've got the Lincoln Memorial in there now for scale. I should have put Independence Hall back in, but at any rate, this is it breaking off. Right, that splash is 50 stories high. You know, let's make a splash, a cannonball. 50. You can tell when these things go off because they make a magnitude 5.5 earthquake that you can feel here. You know, it's really sort of amazing. You know, run it backwards, run it forwards. Great stuff. Okay, so what it does now is it breaks and it's trying desperately to relax itself by creep, but it never does. It's always a cliff. Everywhere that ice flows into the ocean, it's a cliff, even though it's trying to relax by creep. But now it breaks, and then it has to wait till it thins to float, and then it breaks again. If it were a little higher, and how much higher is really, really hard to get at, but if it were high enough, every study that has looked at this gets the same answer, which is then it breaks and it breaks again. And if you remember the retreat at 10 kilometers a week from the Larsen B, it was helped by the meltwater, but this is a system where breaking was controlling the rate, not flowing. Okay, and we published, Byron Perzak was the lead on this with a bunch of us here, and it will go fast. Okay, this is the highest ice cliff on Earth, but we could have a lot higher ones if everything goes wrong in West Antarctica. Okay, so let me do it for you once more. Anybody been to Glacier Bay? Oh, yes, cool. It's fantastic, isn't it? Yes. Okay, so this is a picture of Glacier Bay. That's 100K, 60 miles sort of going in there. When Vancouver goes by in 1794, there is no Glacier Bay. It's full of ice. The ice is a mile thick up about there. Okay, John Muir goes back, makes data that we still use in 1888. It's mostly open. The ice had advanced out to where it's really narrow and shallow. It sat there, it hung on, it had feedbacks that kept it there. There's a lot of things keep it there. When you kick it out, it goes into retreat. This is a map of the retreat and how it got out at the bottom there. It was 1760 to 1780, and then it starts retreating. Muir sees it back up there in Muir Inlet over on that side. And I'm going to take you up to that little tiny corner of this place, and I'm going to look at it along that arrow. And this is what it looked like in 1941. It's calving right at the corner, barely in the picture. 9 years later, okay, and then a little later yet. So that's that little corner of this place, and it goes boom, 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 okay? And now you can go up in the cruise ship, and it just barely makes icebergs. It's this little tiny weeny thing that's gloriously spectacular and scary huge. Right? This is the thickness change. And the little reddish colors up there in the middle are 1,500 meters plus. So it's a mile of thinning. This was locally spectacular. It is globally insignificant. Okay? So we've known this, and we've known it for well over a century. This is how ice ending in the ocean behaves. It stabilizes itself at a bottleneck. There's lots of things that keep it in the bottleneck. It is hard to kick out of the bottleneck. You try to back it up, it flows faster, it rams itself right back in the bottleneck. It's sedimenting to do that, okay? When you back it up a little bit, the land rises under it, and that tends to stabilize it. If you kick it out of the bottleneck, it retreats to the next one. And it's really hard to stabilize it on the way, okay? And if that were to happen, if we were to kick it out of the bottleneck in West Antarctica, it's the same processes in a bigger place. Okay, so this is West Antarctica. This is all of Antarctica. The blue is thickening. There is a fascinating story that we did a lot of the work on here at Penn State. The reds are thinning. And we're going to go over here. We're going to take the ice off West Antarctica. Reds are high. That's the Transantarctic Mountains. So high red. Blues are down to 2,500 meters below sea level. Now, the ice is 4,000 meters thick, so it's got 1,500 meters that can contribute to sea level rise, but it's in a big hole. Okay, this is a rift system. If you're a geologist, this is the basin and range of Nevada. It's spread. The ice wants to, the ice wants to flow along the rift, because there's all kinds of structures that channel that. But it's a ridiculously long distance to go from the middle all the way out to the front. And it has to go downhill ultimately from the surface. And that means the center has to pile up a lot. And when you pile the center up, it goes out there. And it's stuck in the bottleneck. It's all converging vertically and horizontally. Oh my goodness, I drove down to Penn. I came out Saturday morning at 8 o'clock and they were backed up trying to get in. It's crazy. They hit these things. And they don't have a vertical merge, right? We really need to make Thwaites, you need about 3 or 4 decks coming together vertically as well as horizontally, and then that's the real bottleneck. And so what we're worried about is, could this bottleneck slowly retreat far enough that it gets to the point where it loses its ice shelf, it makes a big cliff, and then it falls apart. Okay, so that's the picture. Warming thins, breaks off the ice shelf, it speeds cliff flow, it retreats from the bottleneck, then it goes even faster, and then we're in trouble. Okay, so this is bragging. A lot of this was done by Rob DeCanto and Dave Pollard. Dave Pollard's a Penn Stater. I helped him a little bit. There is basically one model that has tried to put in physics for that has tried to test it against deep time. Can we make ice ages? Can we deglaciate in the Pliocene? Can we do what the ice sheet did in deep time? And that sort of vaguely looks like today. And that's hard. It's stinking hard. I guarantee you this is not the last word. I guarantee you should not use these results as being right. But so far, I think it is still true that there's only one model that has actually tried to do all of that. And in our model, if we avoid strong warming, we're fine. It's slow, it's easy. We've got centuries or longer that we're okay. If we drive strong warming, sometime in the next century or so, we get off the bottleneck. And then it goes as fast as we let it. And we put a speed governor on, which Jakobshavn has already beaten. And so don't count on ours. Ours took 100 years after it gets started to do 3 meters and 3.3 meters of sea level, 11 feet. But we had a speed governor that's not really realistic. Okay. All right. So I can show you a lot of literature. I can quote this chapter and verse of people who have built good models that don't collapse. But like I say, I don't think they've all put in all of this physics. What we do know, beyond any doubt, is if you thin far enough, the ice shelves break off. They don't just get thinner and thinner and thinner. At some point, they break off. Okay, that break off then leaves a cliff, and buried in that slide of Kurt's book are the full tensor, the full Stokes, the extra stresses of that cliff matter. The damage to that cliff matters, because you saw the picture. That was not intact ice. That was damaged. We've done a lot of work, and other people have confirmed this now. The ocean doesn't just stop at the edge of the ice. It's sneaking its nose underneath in estuarine zones. And that can run the melting inland, but basically nobody has an estuarine zone in their model. We don't know how to put it in properly. Okay, and then there's some other stuff. It would take me a long time to talk through this last one. We have done some, right? So this is former students and Sridhar and so on. This is the actual bed of West Antarctica in the one of 2 places that we have really good data. And the dark blue up to the brown is 600 meters vertically. And those are you can see the faults of the basin and range sitting in there. You can see these telltales are 100 meters high and they're 10K long. And oh man, it's just fantastic. We don't have those data for the rest of the ice sheet. We just don't. And where we have them, if we try to take what we know about it from seismic measurements, which are shown there, and we try to put it in the model, there's a fairly broad range that putting the real bed in makes the ice sheet less stable. And this is going to be Emily Schwann's PhD. It's coming. But there's a fairly broad range of parameters that doing this right is actually bad news, right? So the fact that the ice shelves break off, they don't just thin, that there's extra stresses in the cliff, that the cliff is damaged, that there are iron zones, and that there's a spatially variable sliding wall, all of those tend to destabilize. None of those are in most of the models, right? They've zeroed them out, but they all have the same side. Now, they're all really hard to model, and if you put it in, which we tried to do on one of these, it is so obvious that there are holes in your logic that you get beat up, down, and sideways. But by choosing to zero them out because we don't know them, we have put a bias into the system. And we don't know how big it is, okay? So we're right back where we started at the beginning of this, that it's hard for sea level rise to be much less than what the IPCC projects. It is possible to be more. Okay. Now, I served the national academies, and we did this report on abrupt climate change, and then I chaired that one. I served this one. The truth is, if you look for the thresholds in our dealing with climate and energy, if you look for the tipping points, the ones that matter are us. Really, they're societal. Really, it's social side, not physical side. Really, it's when do we decide to get together and solve the problem, and when do we decide we're going to break things and shoot each other, right? And then they're biological. At what point does the Brazilian rainforest burn and not grow back? But of the physical tipping points and shutdowns in the North Atlantic and a few other things, Thwaites is probably the biggest one. And this is assessed pretty well in here, that this is the one that really matters. Okay, so the Corps of Engineers came pretty close to getting $54 billion to build an Ike Dike around Houston and Galveston. Okay, they've got really advanced plans for $56 billion for a Sandy Shield for New York. To do San Francisco Bay and the port of San Francisco is about 120, I think it is. At any rate, 3 U.S. ports is $230 billion. 3 U.S. ports is $700 for each person in the U.S. That's not Miami. That's not Philly. That's not New Orleans. It's $230 billion for 3 ports. As far as I can tell, their budget for getting the sea level rise right is 0. Okay, they do a low, a medium, a high. They pick the medium. They're using NOAA. NOAA is more or less using the IPCC plus a little. That's grossly oversimplified, but that's more or less what's going on. So remember, if we build too much wall, because NOAA said, let's add to the IPCC, we're wasting money. We're wasting ecosystem services. We're wasting recreational services. This is a terrible thing to build too much wall. If we build too little wall, and then we tell people they're safe, they put their lives and their property behind the wall that we built that's too little, and then we do another Katrina. Okay. We're just finishing this up, right? So a few of us worked on this. The US and the UK got together, and we did 50 million to try to figure out what Thwaites will do. 50 million is 0.02% of the cost of protecting 3 US cities. 0.02 for 3 cities, okay? And we have been told, you're done now. Get out of line, you can go to the end, and maybe someday you'll get back in line and get a little more research there, okay? So this is a biased statement at the bottom here in red, but if you want my opinion, the value of research that is being done here is so grotesquely higher than the cost of the research that's being done here that you can't even compare them. It's just laughable. If we were actually sane and reasonable and we started contemplating spending $230 billion on 3 cities, we would be throwing money at these people. They would have to dodge. Okay, be honest. This is ridiculous. So I'll shut up. Sea level rise with warming virtually guaranteed because heat makes water expand and it melts ice. And the IPCC, no chance that they are alarmist, and a real chance that they are overly optimistic. So thank you for inviting me, and we can have a little discussion. Thank you.
Thank Thank you, Richard, for your great talk. As always, very inspiring and mind-blowing. So we have time for questions. So from audience, any question?
Yeah, thank you.
Hi, thank you, Professor Ali. I'm going to bring us back to the economics because you've presented sort of a straw man argument going with Nordhaus, but are you familiar with like the work of Nick Stern? Because it comes down to this argument over a discount rate, and like Nick Stern in the UK, maybe that's why you got some NERC funding. You know, he does raise the alarm saying that, you know, we should invest now because we shouldn't assume that our grandkids are going to be richer. And because he brings in, you know, the catastrophe that could result from climate change. So I just wonder if you've encountered that. And then I'm really curious about the helicopter, who the 10 senators were and how you talked to them and if their perceptions change when you take them up there. What year was this trip?
Right. So it was 2010, I believe. We had Amy Klobuchar, we had Bernie Sanders, Barbara Boxer and Barbara Mikulski led it. We had Corker, we had Rhode Island. Oh God.
White House?
White House. White House. His wife is a marine biologist. She's really good. When the plane door was closed, they were all smart and interested. And when the plane door was open and the press was there, some of them from one side of the aisle were not. So you can get a whole lot of insight in a big hurry there. For one of the truly magical times of my life was sitting in a room in San Francisco with Jerry Brown and Lord Stern and Michael Mann eating takeout Thai and drinking white wine and talking till 2 in the morning. Okay, Lord Stern, if you don't know, he was the head of the World Bank, I believe, and he speaks in paragraphs. He opens his mouth and a perfectly formed paragraph comes. I cannot do this. I am sorry, but there's no chance that I can do this. And so all of this, most of you know this probably better, and you know this better than I do. If you take these integrated assessment models, essentially, if you are a policymaker, you have resources and you can use them now to give people food and clothing and housing. You can invest broadly in the economy to grow for the future. You can target your investment at climate change or curing malaria or something. And the question is, how do you optimize for those choices between broad investment, targeted investment, and consumption now? And they're a tool that attempts to provide guidance with a sort of greatest good for greatest number idea. It doesn't normally have built-in things like justice. And so that's important right away. And they all end up eventually with this idea of a discount rate, which is partially that the economy grows and that lets you solve problems that you left, and partially that we don't care about our grandchildren as much as we care about ourselves. And that's a pure rate of time preference, given a pejorative interpretation. And so sitting in there is this, how rapidly do you do it? You can turn the discount rate into sort of, kind of vaguely, how long do we care about the future? So a 4% discount rate is 1 over an e-folding time of 25 years. So the standard that Nordhaus started with was we care about 25 years a lot, we care about the next 25 years a little, and then we don't care. And now I think most economists have gone to 3%, so we care about 33 years, right? Lord Stern did the radical thing of saying that we actually care about 100 years. So he put a discount rate of 1% in and said and at the moment you do that, the amount of effort that we should be putting into getting rid of global warming just goes through the roof. It entirely changes how you look at everything. Because we emit some CO2 now, but we only care about the next 25 years. we're still sort of in our adaptive capacity. We still haven't had time to wipe out the ice sheet. And if we only care about 25 years, the costs of global warming are really, really small. And then we've just said the future can deal with this. And that usually is based on this idea that they will be rich and they will have all these resources and they can do anything. And so they can cure the problems that we leave for them. And we're headed steadily towards the realization that that's not nearly as true as one would like it to be. We're headed towards the realization that there really is climate justice. There really are issues that are not taken up by, this thing is sort of weighted by the economy. So it's really heavily weighted by rich people. I'm sorry. So there's a huge number of things come into it. The reason I go back to it is because given all of that, the we can grow forever, we're all going to be rich, rich is all that matters, rich solves problems, we only care about the next 25 years, we're still hurting the environment by not doing more about global warming. There's no honest way to look at this that says that we are on track for doing what would be wise for the economy on global warming. And I think that is a very powerful thing, because everything else that I just mentioned strengthens that conclusion. But if you do everything you can possibly think of to get rid of action, we're still not acting enough. So do you want to add anything to that?
I think you should add that to the front of the talk too. Thank you.
Thank you. Yes, other questions. I'm sorry, that was a diatribe, but it is, and I did, this committee that I chaired, Nordhaus was on this, and he interviewed me to see if it was worthwhile serving on it. And we've occasionally interacted since then. I think he was interested because he killed the field that he founded. Because with a 4% discount rate, it never gets extremely interested. And abrupt climate change makes it interesting again.
And I took their classes, Nordhaus and Mendelsohn, and they like to be pejorative, like, oh, we just don't have to worry because Arkansas is going to become the new Corn Belt, like that kind of logic.
Yeah. Yes.
Hey, thank you so much for such a great talk. And my question is to ask if you could reflect more on the assuming of zero values in the model that in some ways I thought was an interesting kind of centerpiece of your talk. And I guess what's behind my question is thinking about kind of what led the scientists to do that. I'm also reflecting on my own work with biodiversity extinction rates, where it often seems like values in the mid-range are the ones that tend to be assumed. So here we have the IPCC. On one hand, maybe they don't want to be controversial, but on the other hand, there's a lot of public credibility and trust in the IPCC for the strength and the rigor and the validity of what they're doing and what they represent. And so I think it's incredibly fascinating about, and here you are with a very kind of open, full disclosure, here are the hard facts, and yet you were also an IPCC insider to some extent. And so can you reflect more on those zero values? It's such a small point, but in some ways, when I think
it's a huge point.
I think it's I think it's like the core of your talk in some ways is what led to that. Because now you're kind of like rethinking that with all kinds of incredibly convincing, impressive evidence. But evidence that's not exactly brand new either.
No,
so
this is very old. So I first participated in the IPCC in 1995. So I was brought in very late because there was a fight going on between the model people and the data people on this topic. And I was a young guy and I had written a review paper that was published in Nature on the topic, and they brought me in. For the third assessment, I actually rode down from Mount Hood in a van with one of the leading European ice flow modelers who explained how they had worked together to make sure that I was not associated with the sea level rise chapter for the third assessment because I was such a nut on these particular topics. And he was sort of glad about this. I helped a little bit with one of the process chapters, but I was not on sea level. For the third assessment says, we have huge uncertainties. They do a good job on the uncertainties. Our central estimate is Antarctica grows for the next 100 years under all warning scenarios. I wrote the text in the fourth assessment that says, oops, it's not shrinking very fast, but it's shrinking 100 years before it was supposed to. Okay, so this is a very long thing. The nicest interpretation, and a lot of this interpretation is right, is that this is because the modelers are actually really good. They're really careful. They're really thorough. They don't want to scare the heck out of people with poorly founded physics. And so they're waiting until they can put good physics into the model. A lot of the modeling groups are doing experiments on what would happen if I break this off. But what underlay the IPCC was still, you read through the text, was the most recent one was primarily models that had zeroed these out. And because they're very, very poorly parameterized, they're very, very poorly understood, that was the choice. Now there's a paper that's getting a lot of play from Byron Berezac. I don't think Byron came over, but at any rate, this one about the estuaries, the warm water can sneak its nose under. He ran a whole bunch of models of thwaites and said it's really hard to kill thwaites unless you let the warm water go under, and then it's real easy to kill thwaites. But nobody in the IPCC suite had warm water going under the edge. They just did. So how to deal with this? And I don't know, any of you, so you can chime in too, because several of you have insights. But I think a lot of it is that they're just really, really good. They're really careful. They're really thorough. They don't want to endorse something that they can't support. But then I would go back to the Oppenheimer, Oreskes, discerning experts. And if you haven't seen this, if my computer were plugged in, I could pull it up. Naomi Oreskes led one that Michael Oppenheimer is on, and they wrote a blog post for Scientific American that is 3 pages that summarizes this book. And the book is serious scholarship. I presume you know it. And the blog post is what you want. And so if you haven't seen it, go looking for something like the book is called Discerning Experts, and I forget what the blog post was called, but it's discerning. Okay, and if you look for Oreskes and Scientific American, Oreskes and Oppenheimer, you'll get it. And if you don't find it, just drop me an email and I'll send it to you. So they say that the way the IPCC has to agree. Every word has to be agreed. And you have to get that agreement past many national governments. Many national governments. And as a consequence, how do you possibly get anyone to agree on something that's based on one data point? Something that is based on fracture mechanics that aren't quite right yet. And that does, and how, in heaven's name, do you deal with a system in which it sits there for 10,000 years under warming and cooling and wetting and drying and faster and slower and up and down and sideways, and then it collapses at 10 kilometers a week? Where are you going to get a data set that you can calibrate a model against that? And if you build a model for that, either you're going to tune it and tune it and tune it and tune it and tune it until you hit that and then it's useless, or it's going to be wrong. I have a minor in metallurgical engineering and material science. I took the broken things course. The professor brought in broken things and we talked about them. And at the end, every person in that room except me was an engineer. They were going to go be a PE and get a job doing real things. And the professor says to them, calculate everything to 5 significant figures, then build it 3 times stronger, because you'll never get it right to a factor of 2. We're within a factor of 2. And we may be within a factor of 2 and not fail forever, and we might fail. And what do you do? Engineering, which is, let's not screw it up, says, don't, as an engineer, you should never get yourself in a position where you have to get this right, because, you know, right? I mean, you know this. If I drop it, will it break? Will it crack? Will it break in 2? Will the handle break off? Will it chip on the edge? Will it smash into smithereens? I can do you a beautiful probability density function for mugs dropped on the floor. Okay, I guarantee you I can. We could do a lot of experiments. We could make this work just fine. Are you going to predict this one? See, and this is the problem. And how then do I write a rule for that when I know it's not right? Put it in the model and take it to the IPCC and say, I want $230 billion for this, times 100. And this is, I'm sorry, this is why you have so many social geographers and not just physical ones. You have to have the physical ones, and you jolly well better keep them happy. But but this is why you have so many social geographers, because now this gets hard.
Well, I mean, that's what's behind my question. It seems to me that the assumptions of the 0 and the centrality of that to your talk from the physical sciences, it's, you know, it's rationalized by, in the face of uncertainty, we just go with the, you know, this zeroing, and then we're faced with the consensus that this runs up against, which then becomes in many ways the as are more important than the physical problem itself. And yet no one was acknowledging that. Sorry about that. So here we have a massive acknowledgement of all the physical problems, but that what I would refer to as a translation problem, understanding the pressures to put zeros in, that translation problem was getting 0 attention.
Yeah.
And as an academic, as a scientist, I find that like stunning. Like, just like, wow, we better reflect on this in terms of public science, what it is, where it goes. And, you know, like you say, it's another side of science. It's in many ways, it's a bigger set of issues and questions, but your talk is just so illuminating because it brings all this out. Thank you.
Well, yeah, I think you do some of this in your department. We do a little of it elsewhere. We could do a little more.
Our time is quite up, then maybe we can have time for last question. Anyone? Last one.
Thank you, Richard, for the scary talk. So my question would be, if Thwaites is the place to worry about, what is the level of monitoring that's happening there now in terms of resolution and coverage?
Right. So remote sensing is getting better. So Shuja is doing unbelievable things with squeezing more data out of existing sensors, and with making sense on them, and with data mining. The healthiness of the satellite constellation, whether the next satellite gets launched, whether we can get more of that, I think is grossly in concern. So whether anybody is going to keep us going is a real question. But the getting on the ground, the U.S. is not going to. The Koreans will do some, maybe somebody else gets in there, but the ability to get on the ground, to get access in there is just going down the toilet. Sorry, that's a technical term. Don, did you want to add?
Really hard to get there.
It is stinking hard to get there. Yeah.
So get there and do day trips, or you can set up a camp and work on the service for maybe a month as long as we wait.
Right. So Don's been there. He got some of those fantastic data, and he was part of this. We used to put in proposals that were before this international thing. We spent 10 years trying to put in proposals to get back to Thwaites, and they kept not funding them. And finally, an NSF official, who I cannot name and I would not, pulled me aside and he said, you know, we have been refusing your proposals and listing causes, but we're just scared to crap out of the logistics. And so eventually we got there because of international that leveraged the logistics, but it was stretching everything to get there. So, and there was a person year wasted on getting turned down for the wrong reason. Sorry. So there's an immense amount of work that really should be done. We had a former student who runs a geophysics company that makes these really sensitive tilt meters that would allow you to look at this estuarine zone, and they've been deployed for a week. Our former student deployed them, but we can't get back to do more of them, right? And they should be all along the grounding line. And to get there, you'd probably need a helicopter off a boat, because if you drove in on a snowmobile, you would fall down a crevasse before you got there. So, so yeah, there's real. So at this point, keeping the modelers and the remote sensors going is far and away the most sensible thing. And if we can keep a satellite constellation, which is the hard part, just making sure that they can do what they do is the most important thing by far. It just blows everything away, and we're just going to have to live with that for now. So keep them happy. I'm sorry, this one is easy.
Thank you. Thank you, Dr. Ellie, again for his brilliant talk. Yeah, this is actually our gift to you. It's a coffee hour mug.
Get a picture.
There we go. Here we
Want
go.
to get the picture?
Yes. Here we.
Listen.
All right. I didn't break it either.